This video is of Lesson 73, Formulas for Sequences, and it is for my pre-algebra classes. So a little bit of review here. We've already learned about arithmetic sequences, so I've given you kind of an abbreviated definition here. Arithmetic sequence means that it has a common difference, and we usually symbolize that common difference with the letter D, where D can be found by taking a sub n. Remember, a sub n just means the nth term or some term, and then minus a sub n minus 1. So n minus 1 then, so think about if this is the 7th term, well then 7 minus 1, this would be the 6th term. So it's the term before. So D is calculated by taking some term and subtracting the term before it. Well, if we rearrange this equation, what we discover then is that a sub n, our sum term, equals the term before it, a sub n minus 1, plus d. So in other words, what's happening in an arithmetic sequence is that common difference, we keep adding it on to a term to find the next term. So it's a little funny in that sense that there's a common difference, but that common difference is what we keep adding on to find the next term. So the equation for this, by the way, is called the recursive formula. We're not going to be using that as much. The one that we're going to be using more is what's called the explicit formula, which is right here. So we're looking for this equation. So the equation, we've actually already learned this. A sub n, so some term can be found by a sub 1, so this means the first term, taking the first term, plus that common difference times n here is going to be our variable. It's going to match this right here. So n minus 1. And as we plug in our numbers, particularly we're going to plug in something for a sub 1, whatever the first term is, we're going to plug in whatever that difference is. We always want to simplify the equation. And we'll see that in just a moment. So here we go. We're going to look at the sequence 3, 6, 9, 12, 15, 18, and on and on and on. So first of all, we need to actually confirm that this is an arithmetic sequence. So there has to be a common difference. So between any term minus the term before it, it needs to come out as something in common. Okay, or you could almost call this a constant difference. So if I take the second term, 6, minus the first term, 3, I get a difference of 3. I take the third term, 9, minus the second term, 6, I also get 3. The fourth term minus the third term, I get 3. The fifth term minus the fourth term, I get 3. The sixth term minus the fifth term, I also get 3. So therefore, do we have a common difference? Well, sure we do. All these together tell me that D, my constant difference here, is 3. We have a constant difference of 3. Now, in order to find the equation, I also need to know not just D, but I need to know the first term. So the first term here, a sub 1, well, the first term is 3. That's just the first number in the sequence. So the equation of this sequence right here then will be a sub n equals a sub 1, which in this case is 3, plus D, which is also 3, times n minus 1. So what I'm going to do now to simplify this is, first of all, I want to get rid of those parentheses, so I'm going to use the distributive property and distribute that 3 in. Remember that 3 has to go to both of the terms inside. So this 3 goes to the n, making 3n, and this 3 goes to the 1. 3 times 1 is just 3. We can simplify this further by combining like terms. This is a constant term, this is an n term, this is a constant term. So I can put my two constants together. Remember though, ladies and gentlemen, and for the most part you guys have been doing a pretty good job with this, that minuses get treated like negatives. So this is basically like a -3. So a +3 and a -3 can be put together. Well, I'm going to go ahead and start with my 3n because nothing's happening to that. And then a +3 and then -3, well, really just are going to cancel each other out, which means this actually is my equation. So a sub n equals 3n. So if we want to find, now let's say some term, like let's say we want to find the, so this is the 6th term. Let's say we want to jump all the way up to the 20th term. So then a sub 20 then, well, we just replaced n with 20. So that'll equal 3 times n, 3 times 20. So the 20th term here would be 60. And that's how we use the formula. This is how we find the formula. This is how we use the formula. Look at another one here. So we'll skip a couple lines, come down. 13, 8, 3, -2, -7, -12, and on and on and on. So again, choose some term and subtract the one before it. So if I choose 8, which is the 2nd term, I have to subtract the term before it. The order here does matter because 8 minus 13 would be a -5. And then if I take my 3rd term, 3, and subtract the term before it, 8, 3 minus 8 is also -5. -2 minus the term before it, -2 minus 3. So this is going to the left, that's going to the left, so together they're going to go to the left a total of 5. And then I'm going to take -7 and subtract the term before it, a -2. Remember, minus a negative though is plus a positive. And so this is going 7 to the left, come back 2 to the right. Well, that's -5 as well. And then last one, take my -12 and subtract the -7 that comes before it. Minus a negative is plus a positive. So if you go 12 to the left and then come back to the right 7, once again we'll be at -5. So what we discover here is that we do have a common difference, but this time the common difference is a negative. And that should make sense. If we're going up, our common difference will be positive. If we're going down, the common difference will be negative. Once again, in order to find the equation, we also need to know a sub 1. So a sub 1 here, the first term, is 13. So now I'm ready to go ahead and find my equation. So a sub n is the first thing in the formula, equals a sub 1. Let's see, can I get, yeah, there we go. I can get both those on the screen. A sub 1 we discovered was 13, and then plus d, but plus a -5 really could just be -5 times n minus 1. And then we need to simplify. So in order to simplify here, we're going to use the distributive property again, but remember, ladies and gentlemen, that you're going to take this -5 here and distribute it. You're going to treat that minus like a negative. So when I distribute this in, this will be a -5 times each of those. So a sub n will equal 13, and then a -5 times n will just be a -5n or a -5n. But then a -5 times a -1, well, 5 times 1 is 5. A negative times a negative, though, will cancel, making that a positive. So that'll actually turn into a +5. All right, now I'm going to simplify it further. Constant term, this is an n term, and that's a constant term. Remember, this is a -5n, though. I'm going to put my -5n first, and then I'll put my constants after that. So a +13 and a +5 Well, 13 plus 5 is 18. So now if we go ahead and plug in, let's say again we want to find the 20th term in the sequence. So the 20th term this time would be a sub 20 equals negative 5 times n. So this time n is 20, because that's what we have there, 20, plus 18. Well, negative 5 times 20, 5 times 20 is 100, and the negative will still be there, nothing to cancel it. Now, if you go 100 steps to the left, and you come back 18 steps to the right, you're definitely still in the negatives. But where in the negatives? Negative 82. So the 20th term, if we were to keep going, the 20th term would be a negative 82. All right, let's go ahead and flip our papers over, no matter how much space you've got left there, just to kind of separate this a little bit. Because we also talked the other day about geometric sequences. And a geometric sequence has a common ratio, which we symbolize with the letter R. So remember, ratios we often write as fractions, so we need to be thinking division here. So last time it was a common difference, we subtracted. This time common ratio, we divide. So the ratio can be found by taking, again, some term, but this time dividing it by the term below. Now be really careful here. Make sure that your n and your n minus 1 are smaller than your a's. Okay. That can be a little hard writing that small in a fraction. Now if I rearrange this equation, what we discover is that a sub n equals r times a sub n minus 1. So whereas last time our constant difference meant that we kept adding something to find the next term, this time our constant ratio means we keep multiplying by something to find the next term. So take the term before it, multiply it by the ratio, you get the next term. So because of this, our equation transforms a little bit. Our equation transforms into a sub n equals, and it still starts with a sub 1. We're still going to start with that first term. But this time, instead of plus, it's going to be times r. And then last time we took our constant difference d. We kept adding d over and over and over to find the next terms. So if I look here, we kept adding 3 to find the next term. This plus 3, plus 3, plus 3, plus 3, plus 3. Down here, plus negative 5, plus negative 5, plus negative 5, plus negative 5. Well, repeated addition gives me an exponent. This time we're multiplying. Repeated addition gives me multiplication. Repeated multiplication gives me an exponent. So it'll be r to the power of n minus 1. So let's look at an example here. 3, 6, 12, 24, 48, and on and on and on. So in this case, if I want to confirm that this is in fact a geometric sequence, I can tell it's not arithmetic, because if I subtract here, I'd get a 3, but then here I'd get a 6. It's not arithmetic. So if I want to see if it's geometric, constant ratio, check that ratio. So I'm going to take my second term, 6, and divide it by my term before, 3. So 6 divided by 3 gives me 2. Take my term 12, divided by the term before, 6, 2. Take my term 24, divided by the term before, 12. The answer is 2. Take my term 48, divided by the term before. So do we have a constant ratio here? Yes, we do. So what we've discovered here is that we have a constant ratio 2. So the only other thing that I need to know in order to find the equation is the first term. Well, the first term is right there, 3. Plug it into the formula. A sub n equals a sub 1, 3, times r, our constant ratio is 2, to the power of n minus 1. Now, there's really not a great way to simplify that, so we actually could stop right there and just allow that to be our answer. So let's say now I've got the first 5 terms. Let's say that I wanted to find, we won't go 20th term this time, that's going to be a bit big. Let's just go with the 10th term. So the 10th term would then be 3 times 2 to the power of 10 minus 1. So this is really 3 times 2 to the 9th power. I'm kind of running out of room there, so I'm going to come down here. So this will be 3 times, and then 2 to the 9th power is 512. So just following the order of operations there. And then finally, 3 times 512 would be 1,536. So what you can see here is, geometric sequences really start growing quickly, don't they? So just 5 more terms out here, and we go from 4 to 8 all the way up to halfway between 1,000 and 2,000 practically. All right, we're going to look at another example here. So for our next one, 2, 4, 8, 16, 32, and on and on and on. So same idea here, the term divided by the term before it. So 4 divided by 2, 8 divided by 4, 16 divided by 8, 32 divided by 16. And sure enough, 2, 2, 2, 2. So do we have a constant ratio here? Yes, we do. This also has a constant ratio of 2. However, instead of starting at 3, we're starting at 2 as well. So my formula this time is a sub n equals my a sub 1, my first term, 2, times 2, the ratio, to the n minus 1 power. Now, ladies and gentlemen, if we think about this here as being 2 to the first power times 2 to the power of n minus 1, we can think about these as being both powers of 2. And so if they're both powers of 2, that means we actually can simplify this. So this would just combine. And remember, when we multiply powers, we add the exponents. So this becomes 2 to the power of 1 plus n minus 1. So in other words, our simplified formula here, well, positive 1 and a minus 1 are going to cancel. This really is 2 to the power of n. So it's not as often that we will be able to simplify geometric sequences, but when we are able to simplify their equations, it's usually going to be when our r and this guy right here match, or at least have some sort of exponential relationship with each other. Not going to come up too often right now. All right, I'm going to draw a line here. We're going to try to fit in another example right there. I want to try to leave this space on the bottom open. I got something planned for it. All right, last geometric sequence, 2, negative 6, 18, negative 54, 162, and on and on and on. So this one's a little different. Notice that it's going back and forth. Positive, negative, positive, negative, positive. You can assume the next one would be negative. So same idea here, constant ratio. I'm going to take my negative 6 divided by the 2 that comes before it. I'm going to take my 18 divided by the negative 6 that comes before it. I'm going to take my negative 54 divided by the positive 18 that comes before it. I'm going to take my positive 162 and divide it by the negative 54 that comes before it. So the term divided by the term before. Well, in each of these, hopefully you can see it's either a negative divided by positive or positive divided by negative. Either way, there's a single negative there that's not going to cancel, which means we know every single one of these is going to be negative. So it's not just a matter of finding out what. So 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18, you can probably guess it, but sure enough, you're right, it's 3. And 162 divided by 54, yeah, again, is 3. So do we have a constant ratio here? Yes. But this time my constant ratio is a negative. So see what a constant ratio being negative does is it causes these values to flip-flop. So every time I multiply by a negative 3, I'm going to end up with an opposite result. So this one was positive times negative 3 gives me a negative. Times negative 3, back to positive. Times negative 3, back to negative. My first term here, again, is 2. And so my formula then is going to be a sub n equals, my first term is 2. Now here, I'm not actually going to put a times dot. Because this is negative, if I put a times dot and then a negative, sometimes that can kind of look like a minus. So one of the safe things to do when we've got a negative is to put in parentheses. Now here's the other side of it too. Because we're going to put an exponent on this r, we need the parentheses as well to group the negative with the 3. So when I put my n minus 1 up there, then this n minus 1 is happening to the entire negative 3. So just to illustrate the difference there, keep in mind that if you had a negative 5 to the second power written like that, this would actually mean a negative 5 times 5, and so the actual answer should be a negative 25. But if you want to take the entire thing and raise it to the exponent, we express that using parentheses. So then this would be a negative 5 times itself, which would give us our positive 25. So just be aware of that. When r is negative, you will have to use parentheses around that negative r, that is negative. And so that actually cannot be simplified nicely. We stop there. That's good. So the last concept here, let's go ahead and do a dashed line across our page, is a special sequence that our book wants to introduce you to, which is called triangular numbers. And so the idea behind triangular numbers is we just start with a single dot. So how many dots do I have there? 1. But then we move on and we turn this into a row of 2 dots, and we make a triangle 1 dot above it. So the base of 2 dots and then 1 above it. So it makes a triangle. So how many dots do we have now? 3. Now if I move on and I have a base of 3 dots, then next we'd have 4 dots, or excuse me, 2 dots, and then we'd have 1 dot up top. We've got another triangle here. But how many dots do we need to make up this triangle? 6. So my first triangular number is 1. My second triangular number is 3. My third one is 6. And if we continue this, so if I have a base of 4 dots, the next row would be 3. Then after that would be 2. And finally on top that would be 1. This is like bowling pins. So how many bowling pins do we have? Well, if you go bowling, there are 10 bowling pins. So our fourth triangular number is 10. We'll just do a couple more here. 2, 3, 4, 5. So if we have a base of 5, the next layer will be 4. After that will be 3, then 2, and top it off with 1. There's my triangle. So how many dots do we have there to make up 5? Well, you know that this going down to the 4 is 10, plus 5 more is 15. And then just one more here. 1, 2, 3, 4, 5, 6. Next row, 5, 4, 3, 2, 1 up top. And so we already know going down to the 5 that was 15, plus 6 more is 21. So, ladies and gentlemen, what I hope you're kind of seeing here is that we started off with 1 dot. And then basically we added a row of dots below that had 2 dots on it. So we added on 2 more. So 1 plus 2 gave me 3. Then to find the next one, we basically took this, which is right there, but added a row of 3 below. So we added on 3 more. Well, 1 plus 2 plus 3 is 6. And then we took this one that had 3, and there it is right there, but we added a row of 4 below it. So we added on 4 more. Here we added on 5 more. Here we added on 6 more. So triangular numbers are special in that they really are the sum of consecutive natural numbers. So 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4 plus 5, 1 plus 2 plus 3 plus 4 plus 5 plus 6. So if we want to find the next triangular number, just add on 7. So my next triangular number, if I were to make the same pyramid, the same triangle of dots, but this time 7 is the base, there'd be 28 dots total. If we want to go to 8 dots, what if we had 8 dots across? Well, add 8 more, 36. So the 9th triangular number would be 45. If you have a base of 9, it'd be 45 dots total to make it. And we'll go just one more here. Just make it nice and round and 10 here. We'd be up to 55 dots total, which is why we're not going to spend our time drawing that. You could, but we're not going to take our time to do it. Ladies and gentlemen, this is all fine and dandy, but what if I want to jump ahead? Well, this formula is neither arithmetic nor geometric, but it does have a nice, neat formula. And actually, there's 2 different formulas you could use. The one, I believe, I forget, I haven't looked at the book in a little while, but I believe the one the book uses is this one right here. So you'll take the number of dots, multiply it by 1 more than that number, and divide the result by 2. Now, when I learned this, the formula that I memorized was n squared plus n over 2. So you take the number of dots you're looking for, square it, add on the number of dots that are there, and then divide the result by 2. If you think about distributing this n in, you'll discover that these 2 formulas literally are the same thing. So it doesn't matter which one you memorize. Just pick one. So real quick, just to kind of finish off here, let's say we want to jump ahead and you actually want to find the 100th triangular number. So what if I have 100 dots across the bottom and I work my way up? How many dots will I have total? So if I think about this, do I want to do 100 times 101 and then divide that by 2, or do I want to square 100 plus 100 and then divide that by 2? You know, I think I actually would rather use this formula personally for this one. So I've got 100 squared plus 100. I'm going to divide that by 2. So 100 squared, so 100 times 100, that's going to be a total of 4 zeros for my answer, so 10,000 plus 100 over 2 equals 10,100 divided by 2. So 10 divided by 2 is 5, so 5,000. And then 100 divided by 2 is 50, so 5,050. Oh, the why I'm writing it small, that's a good question. So 5,050 would be my 100th triangular number. Let's also real quick here. Let's say, what if we just want to find the 20th? So what if I just have 20 dots across? So 10 dots across is 55. So this will be twice as many dots across. So what will that look like? Well, maybe we use the other formula for this one. So 20 times 20 plus 1 all over 2. So that's 20 times 21 over 2. 20 times 20 is 400. And then one more 20 would be, well, actually, you know what? Let's make our lives easier. Let's reduce before multiplying. So that'll be a 10, that'll be a 1. 1 on bottom means it's a whole number, so it's just 10 times 21. So 210 dots. It's a big jump from 55. Just double the number of dots on the bottom, and you more than double the number of dots total. And that, ladies and gentlemen, is our lesson.